I should see some kind of audio here. Oh, there you go.
Testing, testing, audio.
I'm not seeing on this screen here, but you got your recorder on, right?
Yeah.
Okay, I'm gonna hit record. Hope everything's going good. I don't quite understand why I can't get the bar here. Okay, any questions from last week? Oh, yeah. I think we have to get it from both sides. Let me try this side first only. Okay. Any questions from last week? I'll hope that the spreadsheet, maybe that'll jog your memory too. I think this is where we left off with the spreadsheet. I don't know what the N is. Okay, in summary, we have downloaded a spreadsheet that I call software that has basic PBT properties that we're going to use throughout the semester. Z factors, viscosity, compressibility, pseudopressure, which we're not using yet. And then I downloaded another software module last week. And I have too many things here. Gas utilities, right? This is the one you got added last week. And we're going to use a couple of these tonight. Like gas density and gas V sub G and original gas in place, we're going to use. But basically, we downloaded this so that we could use, calculate well stream gas gravity given the information we have at the separator. Two different ways. If we have complete information, that would be the gas gravity from the first and second and third stage separator, the third stage separator being the stock tank, and we get measuring the gas gravity of the vapors, and the gas oil ratio for all those three. And that's on the that's on the spreadsheet when I go back to it. And then we looked at it if we use correlations with the information we generally have when we're in the oil field, which is the pressure and temperature of the first stage separator and the API gravity of the stock tank liquid and the gravity of the gas leaving the primary separator. The general situation, those are the only two things sold, and so those are the only two things measured. The gas gravity and the oil API gravity. Both of those enter into the calculation of what the purchaser will pay for that fluid, gas or oil. No questions on any of that? Okay, so like I said, tonight we're going to look at a couple of these other functions. And again, I think that, I don't know why I've got this page right here. Is that the 1.8, 1.8?
Sir, when you said you made changes from last week, that was not changes made after class last week, right? So we don't have to re-download the one from...
No, I have not done anything. You did see some other modules in there, and that's because this book of mine, I started with the one I was using last year. So you saw something that looked like standing oil. And some of chapter 1, right after we get done with viscosity and compressibility, goes into some oil field properties. As if you would have had a volatile oil, and some of those are handy for calculating or estimating the bubble point of a volatile oil reservoir. But we're going to not really concentrate on oil reservoirs. Remember, all hydrocarbon reservoirs produce gas. That's about, and so, I mean, I could teach natural gas engineering for volatile oil reservoirs, because we still have to deal with all the gas. But basically, from, you remember that last case from the phase envelope PowerPoint, the general case that we're going to talk about this in this course is not a dry gas reservoir, but a wet gas. A wet gas is differentiated from a condensate reservoir in that the reservoir temperature is above the Kreiskonen curve. The reservoir fluid will always be gas through its state of depletion. Liquid appears because when it's brought to the surface, it's brought to a much lower temperature, and so liquids condensate out of the oil. In industry for the rest of your careers, you're going to hear this term all the time, condensate reservoir. And it's like you and I saying we believe in God, but does that mean we believe the same thing? It doesn't, because what a condensate means to a production engineer and what condensate means to a reservoir engineer are two different things. As a reservoir engineer, a condensate reservoir means its reservoir temperature is below the critical temperature, and so during the path of depletion, it will travel through the dew point. Much more complicated situation as far as reservoir engineering is concerned, because you have liquid dropout in the reservoir and it changes all your flow equations and it changes your volumetric equations. So we're talking about basically the more simple case, and of course the simplest case is a dry gas reservoir where the gas is primarily methane. No liquids come out of it whatsoever. It just comes up the wellbore, it's still methane, it goes to the separator, maybe a little bit of water drops out of it, but the hydrocarbon phase never changes, and it goes straight into a sales pipeline. Almost too simple to deal with. So we will work with the situations where we have some liquid production, and we're going to have to entrain that back into the well stream so we can see what our reservoir fluid looks like. So these last two problems we did in class at the end of the hour last night, we'll use over and over again. In fact, we'll use them right away as we look at the next couple things we're going to do. Now that's almost big enough, I don't have to go full screen. So B sub G is the formation volume factor. You'll see other definitions in the book, but in my opinion, it's always reservoir volume per standard volume. In other words, if I took gas at high temperature and high pressure, and I put it in a canister and I brought it to the surface, how much is it going to expand to? So the reservoir volume per standard volume is going to be a number bigger than 1 or less than 1.
Bigger than
Less than
For gas?
How many think it's going to be less than 1? How many think it's going to be greater than 1? Okay. How many people think that pressure in the reservoir is going to be greater than the pressure at standard conditions? How many people think that's going to dominate that equation on your PowerPoint? So is it going to be less than 1 or greater than 1?
Less.
Less than 1, okay. Because pressure, let's say it's 5,000 pounds. What's pressure at standard conditions? 14. What's 14 divided by 5,000? There's no other numbers in there that are going to change it. Now, if temperature was in degrees Fahrenheit, it could be a big ratio change, but it's in degrees Rankine. That's why I always use a capital T. And so even though you may have a 100-degree shift, by the time you add that to 460, the relative difference in temperatures don't change it. And Z, the widest range of Z's we ever see is like from 0.4 to 2. So again, unless your reservoir is at a very low pressure, your B sub G is always going to be. And then you can see that in my calculation of original gas in place, which is what OGIP stands for. And currently, a lot of people call this OGIP. I don't really support that kind of slang, but you do hear that, so I want you to know that that's what it's originally, what it's called quite a bit. And that's opposed to just GIP or gas in place, because after you produce the reservoir for a while, you'll have gas in place, and it will be equal to what was originally in place minus what you produced. And so this number B sub GI is the initial formation volume factor, because at any lower pressure you would have a B sub G, and it would be the current formation volume factor. So the O in OGIP, original, corresponds to the I subscript in the formation volume factor. You only get original gas in place when you use the initial formation volume factor. Other terms we're going to use tonight for the rest of the chapter is S sub G. Who can tell me what that is?
Original gas in place.
Huh?
Original gas in place.
No, the original gas in place is OGIP.
The G.
What's S sub G?
Saturation.
Saturation.
Gas saturation.
Gas saturation. So, I realize we got some other disciplines in here. I wonder if I can pull up a picture of porous medium. Which one do we like? This is good and bad. It shows porosity, and that's what I want to talk about, but it doesn't show any permeability. But well, so when we're doing reservoir engineering calculations, we're neglecting everything you see in the picture, which is rock. Okay? Because by and large, the rock doesn't change. But what's in the rock, if it's gas, it's going to, as it's produced out of the reservoir, it's going to expand as the pressure is reduced. Now, there's almost always another fluid in there. I usually call it connate water or water, but there's a water saturation in addition to the gas saturation. Typical gas saturations are 20, 25, 30%. And typically what that water does is coat the surface of the rock. You can see there's a lot of surface area in porous medium, okay? It's not too dissimilar than your kitchen sponge. Doesn't look like it can hold that much water, but if you wring it out, of course it's pretty hard to wring out porous rock, but then you know that a lot of fluid comes out of those pore spaces. Even when the sponge has been sitting there for a while, and there's not the holes in the sponge don't really have a lot of water in them, but still the water that coats the surface of the inside of the pores of the sponge still holds a lot of water. So even a sponge that's been drying out, you can still squeeze it and wring it out. That's that initial, I'm going to use like 3 different words here, they all have different meaning, but you'll hear them as synonyms. Initial water saturation, connate water saturation, and irreducible water saturation. Sometimes they can be equal. And for the simplest case, your initial water saturation and irreducible water saturation are going to be the same. Now let's just leave that picture up for a second. The important thing is that when we're calculating the gas in place, if we know the porosity. Now, how constant is that porosity across this rock? Is it the same everywhere?
No.
No. it varies, but that's not a problem. Because we can use statistical methods to average it. So we have tools, called logging tools, that we run in the hole specifically through a formation to measure this porosity. And sometimes we use a coring bit that goes down and actually comes up with an upright cylinder of the reservoir rock that we can take to the laboratory. How many people here have been in our laboratories? Okay, so you've seen that we can make measurements on rocks. And one of the things we can do is just, we can pump a fluid in there and see how much fluid we can pump in there. And if those pores are connected, and that's why I don't like volcanic rock, the pores are not that well connected, so it's not the greatest illustration. Then we can tell what the connected porosity is. So flashing back to our static original gas in place, we're looking at two things already. We're looking at porosity and we're looking at gas saturation. So phi, and if you never need to type it, that's your, if you change your font to symbol and put an F in there and it's a lowercase, you'll get a phi. So we always use that phi symbol for porosity on the internet. Okay, so let's look at some other things that are here. Edit this. I don't want to. H is what?
Thickness.
Thickness or formation height, okay? Now, I kind of started with what's inside the rock, now we're working on with the bulk volume. A is what?
Area.
The area, okay? And what is 43560? Square feet in an acre, okay? So if my area is in acres, 43560 just converts it to square feet. And if H is in feet, I have cubic feet. So that gives me a bulk volume. Porosity is maybe 6%, maybe it's 12%, maybe sometimes it's even 20%. But the porosity is the pore space. So I have to reduce my bulk volume to my pore volume with my porosity term. And then not all that porosity has gas in it. Typically those pores are coated with water. And if I did a measurement of how much of that was saturation of gas and saturation of water, again, that number is usually about 20, 25, 30%. Depends a lot about how deep it is, the hotter it is. Sometimes it cooks off some of that water. And in some cases where gas has migrated in recently, the water saturation could be 40 or 50 or 60%. I'm going to talk about this right away. Which means that it is not irreducible. And that when you put this well on production, it'll produce water and gas. And in Oklahoma right now, there's kind of a boom into what they call dewatering projects, where they actually try to drill into reservoirs that used to be avoided because they produce so much water, and they found out that they produce a lot of this water off, and they can actually reduce the water-gas ratio and get a lot of gas out of these reservoirs. So that's kind of an unconventional drilling technique or production technique that's going on in Oklahoma. It's called dewatering. Because it used to be when you test these reservoirs, they produce too much water, and we think that that water-gas ratio would stay constant. And if you ran out the economics at a constant water-gas ratio, it was going to cost more to dispose of the water than it was going to be to have the revenue for the gas. But somebody goes, let's just try producing this for a while and see what happens, and they got lucky. So now we have a whole new boom due to someone taking a chance. Okay, then we're left with our final fluid property. How much is that gas going to expand? And so when we divide by reservoir volume per standard cubic volume, in the numerator we have the reservoir volume. We have the reservoir volume of the gas. So when we divide it by reservoir volume per standard cubic volume, the two reservoir volumes cancel out, and we get the standard volume. Now, this is going to give me the original gas in place in what units?
BCF. SCF.
SCF, standard cubic feet. And the reason it's in standard cubic feet is you look up above, B sub G is pressure at standard conditions and temperature at standard conditions. This textbook likes to use 14.65. Most of the U.S. custody transfers currently use 14.73. Other countries use 1 atmosphere, which is, I think, 14.69, okay? So we're just going to use 14.65 because a lot of the original work in this textbook was based on a lot of laboratories done decades ago, and they just stuck with PSC at 14.65. It doesn't have too much difference on any of the outcomes. It's lost in the third or fourth decimal place. Any questions on, now, of course, if we're calculating the original gas in place, oh, I know, before I leave that last topic, how do we sell gas? By what units? MCF. And that's a misnomer too, because we usually sell it per million BTU. There's about 1,000 BTU in an MCF, so we usually sell it by million BTU. But let's forget about that. Let's pretend that we do sell it by MCF, because that's what you see in the newspaper. But when you really get down, if you're in midstream and custody transfer, you're probably selling it by million BTU, and you're probably giving an extra compensation if there's any liquids involved. But by and large, we sell it by MCF. So when I calculate gas in place with the SCF, I may divide by 10 to the 9th immediately and get BCF, because that's how much gas approximately is in a reservoir, is on the BCF range. So we have to watch our units. This is an SCF. We never use SCF, but it's very straightforward because everything is height is in feet and area is in square feet. So we start with cubic feet and work from there. You'll see things like people moving the decimal place over 3 points on the B sub G. You'll see things like, instead of 43560, 43.56, which is, you should recognize right away that that's going to give you your gas in place in MCF. I'm just warning you of all the pitfalls that you're going to see, not in this textbook, but in your work. Now, I said by and large that rock doesn't move too much, but we actually have to account sometimes for the compressibility of the rock as the pressure drops inside of the core, but we definitely have to account for the compressibility of the gas itself. Now, CG is fluid property, like the other 5 fluid properties that we're looking at are a function of pressure, temperature, gas gravity, and impurities. So it's something that we can calculate using our software at any point in time. By and large, the gas compressibility is much larger than the other compressibilities involved, typically water and formation. So it's usually an order of magnitude higher compressibility than those other compressibilities. But the total expression here would be SGCG plus SWCW plus CF. And you don't have to write that down. The concept of you multiply the compressibility by the saturation is what we're carrying back to this approximation. So we're approximating in the work we're going to do in this class in Chapter 6 and Chapter 9. We're actually probably going to get started on Chapter 6 tonight. We're going to need a compressibility term, and anytime you see CT, total system compressibility, we're always going to approximate that with the product of the gas compressibility and the gas saturation. Now, I don't want to scare you away. Oops. I meant to shift it. This is an appendix of a SPE paper, and the green are for oil equations and the red are for gas equations. The only reason I'm putting them up there is I want to show you where some of these terms get involved. You don't have to memorize this slide. But the fact that we're going to use dimensionless terms in Chapter 6 and Chapter 9 makes this slide appropriate from an introductory standpoint. The first point I want to make is where we're going to see some of these numbers. So you're going to see this product frequently in our flow equations. Basically, we have a dimensionless time and a dimensionless rate and a dimensionless pressure. And we have models that calculate those, and we try to fit the actual data to those models. And if we get a fit, then from the x-axis match and the y-axis match, we should be able to get one of the parameters in these equations, and hopefully we know the other ones and we can solve for the system. It's easy to say, but it's actually hard to do. So there's our dimensionless time is always going to have a viscosity, compressibility term in it. Our dimensionless rate equations are always going to have a delta pseudopressure term, and we've hinted on that a couple of times. Pseudopressure is an integration of the things that change with pressure because they're not constant. That's the Z factor and the viscosity. But given pressure, temperature, gas gravity, and impurities, there's a one-to-one correspondence with the pseudopressure. We can easily calculate it. So when you see pseudopressure, realize that it's just a touch or click away from being calculated. It's not a difficult term. Also, I want to run a little bit about the history, because this is going to impact us when we're working these problems. Before we had computers, and I can remember those days, we used to use approximations because pseudopressure was hard to calculate even though we knew it existed. So we took, if it was a high pressure gas reservoir, we used to use the pressure approximation. If it was a low pressure gas reservoir, we used to use the pressure squared approximation. And you'll see that our author here will drag us through those other techniques. And on his tables of equations, he'll have a pressure solution, a pressure squared solution, and a pseudo-pressure solution. And especially in Chapter 6, when we're doing transient pressure analysis, we'll do all three of those. Knowing what we know now, that pseudo-pressure will always give us the most correct solution. But it doesn't hurt to work the same data over with a couple of other solutions and some other approximations. And then after a while, we'll drop that. The author kind of beats that to death. Because, like me, he lived through it.
What does the pseudo pressure physically mean? Like pressure, we have definition, we have the concept. Conceptually speaking, what does the pseudo pressure mean?
Darcy was a groundwater hydrologist. So we use his name when we talk about the ability to flow fluid. And so what he did is he ran a sand pack and he changed this. He could use diatomaceous earth or we see the sand in the Canadian River, when we drive over it all the time. And he put a pressure head across that pack, and different types of earth would flow more or less water. And so that he gave that as an intrinsic property and called it permeability. Now, he was running water through that. And so so he found that it was proportional, that the rate was proportional to the pressure difference, okay? Now, if we're doing that with gas instead of water, it isn't no longer proportional to the pressure difference. But if we augment pressure to account for changes in viscosity and changes in compressibility, we can get this new term, pseudopressure, that now obeys Darcy's law. So it's a back calculation of what works. So an author that was trying to figure out how to apply all the fluid flow equations, kind of like the ones on the left-hand side and lower part in green, that would work for liquid flow, he tried to come up with something that was related to pressure and could be calculated given the fluid properties, and he did. It's pseudopressure. So pseudopressure is this magic snake oil that, when used instead of pressure, allows us to use all the liquid equations that we used to use, because in the early days we only produced oil. Gas we just invented. I'm talking about before I was born. So there's a lot of different types of equations that are very useful, but they were all generated for liquid flow. So we just found out that if we use pseudopressure instead of pressure, we can use all those equations. We don't have to reinvent equations. Is that a sufficient answer?
Yeah.
Okay.
Thank you.
So there's actually no useful equations on this. Dimensionless linear flow, like how these works if you're really trying to make a calculation for rate. So right here, don't write anything down right here. Okay, this is just introduction. This is chapter 9. This will be the last 2 weeks of class. Just to show you how we can manipulate this. Here I have dimensionless rate as a function of dimensionless fracture conductivity and dimensionless cumulative production. But dimensionless rate, dimensionless finite conductivity, and dimensionless cum all have definitions. Here's dimensionless cum, here's dimensionless finite conductivity, and here's dimensionless rate. I could manipulate this all around so I could have rate as a function of all those variables. But it gets kind of complicated, it's not very useful. What I really would like to do is only on a type curve lay out what the dimensionless solution is going to be, shift my data on a log-log plot so everything becomes dimensionless. There's no, once you take the logarithm of these terms, they're already dimensionally unified. Then you can come up with one solution. Try to see if your data looks like it, if this part of the curve versus this part of the curve. I realize this is hard to follow without looking at the curves. This is just introduction to where we're going. Okay, but the reason I put this slide up here is that these are the kinds of things that we're going to be looking for. In addition to the ones we look at from, I'm going out now. Instead of just looking for static problems, original gas in place is static, okay? Doesn't change. But what we're most interested is in dynamic problems. Chapter 1, basically everything is static. Chapter 6 and 9, everything is dynamic. We're talking about flow or pressure, or transient pressure analysis or transient rate analysis. So that transient term is the dynamics. And we can learn a lot more about the reservoir knowing its dynamics than we can about its statics. We could determine that there was a TCF, that's a trillion cubic feet gas reservoir, just by running a log in the well, okay? But it may have no commercial viability if the permeability is so low that it can't flow. And actually, this rock we got here is a prime example, because this, I can recognize this is volcanic, but volcanic rock is really great for showing porosity, but none of those pores are connected inside. It has very, very little permeability. So, and another term for rocks of this type in general is vugular porosity. So when people say vugular porosity, you know to leave the room, because it looks good as far as gas in place, but it's the ability to flow gas through the porous media as it makes its way to a well or even a fracture interface is negligible. So these types of wells look good to the eye, but they're not good commercially. Okay, just I'm looking down at my notes. How many people have already uploaded their picture to D2L? How many people have not? It makes it really difficult for me when I get an email from you if I can't put a face to the name. So I kind of request that everybody put their picture in D2L. I bet you everybody here has an iPhone or a webcam. So this can be like a 10 to 15 second operation. Okay. It doesn't have to be a formal picture. It just helps me put a name to the face when I get an email. Or when I'm looking at the roll or anything else. And I'm not saying I'm going to learn your names, but if I have any chance of learning your names, I'll have a better chance of learning it if I can put a face to the name. Okay, so where are we going from here? I'm a spreadsheet. Now we'll do some calculations, and we're just going to do. We're going to stick with this problem we did. I think this was the Sabine gas reservoir. In fact, everything we've done in class is on this one gas reservoir. It's the one where we did the piston, calculated the Z factors. We modeled the gas gravity to fit that data and calculate the gas gravity. Wasn't that problem 1.3? Yeah. So what did we? Yeah, we calculated using goal seek or solver. You remember? I realized this was 2 weeks ago, so maybe you don't remember. We ran it. It looks like separator gas gravity. Got that data, and then where am I again now? I'm in. Which ones are? Yeah, here we go. 1.8. Yeah, for some reason I got this N, which I've forgotten what that nomenclature means. This looks like something we did in class last week. And then I think 1.9, okay, 1.8, we were actually given all the data. And in 1.9, or did we do it twice here? And here's actually 1.9. We were given the GOR1. See, these numbers match. And the gas gravity of the separator match. The API of the liquid pretty much match. But instead of giving R2, R3, G2, and G3, we were instead given the separator temperature and pressure, and then using a correlation, we got a gas gravity that way. Using your software, right? This is all reviewed. Now, let's, what is this? Well, this is my error. There's only a 0.05% error in calculating using correlations than in using a calculation with all the data, okay? So, correlations are important. Some good engineer did a good job of getting enough data so the correlations work. And in many cases, this is the technique you're going to use in the field to try to get an idea of what the reservoir gas gravity is so we can calculate these fluids. So let's just play for a little bit. I'm going to give you this stuff. And let's look at, let's make up a reservoir pressure. Who wants to make it up?
5,000 pieces. 5,000 pieces.
5,000. Very good. So few people can read my mind. Okay. I'm just going to put PSI. And I'm just going to assume for all my problems that the difference between 5,000 and 14.65 is so great that I don't really care if that's PSIA or PSIG. In any problem you're calculating, you'll be explicitly given. Okay, let's make up a reservoir temperature.
180.
That's an excellent. And I use this nomenclature right here, and because when I started writing, and actually, I've always done a lot of programming because when I started work, I found that every time I left the boss's office, he was one of those what-if guys that says, well, what if this is different? And so I'd make all these calculations, but then I'd have to change one number. So I found out early that it was advantageous for me to learn to program all my solutions. Back then it was with Fortran. But, you know, I had some simple I/O statements and it did all the calculations. And that way, if I wanted to run a bunch of numbers, sensitivity, I could do that. So I have these symbols that I'm going to use in spreadsheets because if you're reading my Visual Basic, I'll be consistent with these symbols. So that's why I got T-res right here. And I'm going to operate the same way the author of the first set of software, which was not me, it was an engineer at Louisiana State University. But what I've done is what I learned from them in Visual Basic and then what I used to know and how to do it in Fortran. 160, is that the number I heard? Okay.
80.
And that's going to be degrees Fahrenheit. And if you don't know how to make degrees, you just superscript your 0, your lowercase o. Let's give our reservoir an H. Who wants to make up the H?
30 feet.
30 feet. And then how about the porosity?
10%.
Haven't you already made up some numbers? You're not going to let the other class, the rest of the members of the class, did I hear something?
Nobody is speaking, so.
Huh?
25%.
25%? It's possible.
15.
Well,
Play Price is Right.
here's where I want to go with that. I have fun with this class, as you can tell. Does everybody know what I mean when I say low-hanging fruit?
Yeah.
Okay, well, you don't. All the reservoirs that had 20% porosity, and there are some that exist, they're all depleted because they were the low-hanging fruit. And so it doesn't do us a lot of good to study those reservoirs because they're gone. So everything I look at has 6% porosity. But let's go with 15%. Let's head your way a little bit. Okay, how about a water saturation? You can only make one contribution to this here. Anybody want to guess what a reservoir's water saturation is?
36.
36? Okay, so what's the gas saturation?
25.
course, and unless it's specifically stated, it's always going to be equal to 1 minus the water saturation. Okay, what do we not know now? We're going to try to calculate the original gas. Oh, how about area? This is tough on the international student. We typically look at 640. Why do we look at 640?
Section.
It's a square mile. And why do we drill 640s?
That's what the state units are. Typically it is.
Yeah.
And how did that come about?
Sections.
The Swedish settled it, they divided the state into square miles and go and take.
Yeah, so a lot of it's just historical, but our road system lets us basically have access to every square mile. We don't have access to a subdivision of that or something like that. And when we were drilling low-hanging fruit, we found out that we could actually deplete 640 acres. Nowadays, even with multi-frac horizontals, we still drill 4 or 5 wells for 640. But I would say that you would not be frowned on if someone asked you what your gas in place is, and you said, well, this is our gas in place for 640 acres. That'd be an acceptable answer. We normally don't know the acres. Let's do another search up here. I love images. There were some right there. I don't like these ones. I'm really being picky here, guys. Okay. I'll go with this one, as long as it clears up. There we go. So, by and large, a reservoir is not a brick. It doesn't have constant thickness, and it doesn't have limits that are rectangular or orthogonal in nature. Most reservoirs vary in their thickness, okay? But any volume can be represented by an average thickness and an average area. Okay, so here the light blue versus the dark green might show where the sand pinches out. This looks like a typical anticline. A lot of our reservoirs, especially our low-hanging fruit, are anticlines. Okay, so we don't want to get the idea that all of our reservoirs are rectangles. They're just like you see when you drive by an outcrop on the highway. They change in thickness, they come and go. They have structure to them. How many people have been on a geological field trip? Okay, too bad for the rest of you. You're gonna have to drive through Colorado or Utah, and then it's just an open textbook of geology, or the Grand Canyon. How many people have been to the Grand Canyon? There you go. A lot of geology there. Okay, so let's, what are we missing to be able to calculate our gas in place?
DG.
Okay? And are we ready to calculate B sub G? Let's try. I'm trying to get my
What were the symbols you
Software.
were using? V.
gas BG.
PI.
Mine.
PI. Initial version.
Well, it looks like we are, because it's gonna
T-res.
calculate the Z for me, you see that?
And then that's phi, which is an
That's
F.
pretty clever here. Pressure, 5,000, temperature, 160.
That's G.
Gas gravity, okay, we're gonna go with this gas gravity right here, 1.09. It's our laboratory it's our one calculated without correlations. And as far as we know, there's no impurities. But now that I've done that, I'm gonna back up and I'm gonna make myself a table. And this is important, what I'm going to tell you guys right now. I just happen to know the order here. Okay. Why is what I just did there important?
You can run a sensitivity on it based on the impurity. So you can make an adjustment as you have some particular amount of nitrogen or CO2.
Yeah, so if I have some more information, this spreadsheet's already ready for me to rock and roll. Now, here's one that you're all gonna get wrong, okay? Maybe that'll give you a clue. If I have 10% nitrogen, what number should I put right here?
0.1.
ppm, in terms of ppm.
You're wrong.
0.1.
That'd be 1%.
0.1.
I have 10% nitrogen, what should I put here?
You're looking at the-
Okay, so
0.1.
you're never gonna guess it. So we have to kind of look at our VB.
Which function are we doing?
I didn't write this page, okay? I would have written it a little bit different. Look at what they do with their first 3 lines of code. What are they doing? They're converting whole percent to mole fraction. You see that? All the calculations are actually done in mole fraction. So if I have 10%, it's going to do the calculation with 0.1. But when it's prompting me here, I would actually put in 10%. Okay? This would be the wrong number. If I hit 10 with the percent, Excel sees that as 0.1, doesn't it? And then it's going to divide it by 100, and then it's going to say the amount of nitrogen impurity is 0.001. Okay? So this is about the only pitfall with the software there was, and that's because I didn't write it. So for our case, it's 0. It doesn't matter if we use 0% or 0, because it's 0. Okay, so now we have B sub G. So is that number bigger than 1 or less than 1? You already knew that, though, didn't you? Okay, how about original gas in place? I think I have a function for that. There it is. So I click it, I double click it, and you see that I don't have any prompts? Does everybody see that I don't have any prompts? So then I come over here, once I have that much in the window, I can hit F of X and I get my prompts. Now that's not the only way to invoke that. I can go F of X and then go user defined and then find my function. I'm just paging down until I find it. I'm not doing a very good job. Here it is, original gas in place. But if I can remember what it is, I can do it that way. So here's my gas saturation, my porosity, my height, You see, I got porosity as 0.15 or 15%.
Yes.
I don't divide my numbers
Okay,
by
that's
half.
true.
And I actually am giving you a hint to what I want my area units as, because I'm telling you the units for area, acres. How many acres? 640. And B sub G we got previously is this number above. So I'm going to immediately write down SCF. Now, I can divide that by 1,000. And, oops. And get that in M. Technically speaking, we should choose SCF, but I don't hardly ever see in oil field anybody write MSCF, but it is 1,000 standard cubic feet.
He's got 160, that's why it's different. Oh, yeah, he didn't hear him. Yeah.
I avoid using million cubic feet. It's just too confusing. But a lot of purchasers that are buying want to know how much gas is sold a month. You'll hear them talk about millions. That's just too many. So we don't really use SCF. This is how much I can sell. And I don't mind BCF. And that's not a very big reservoir. So why do we not have very much gas? What is small here? Probably at 30 feet. Let's change that to 300 feet. And then we can approach a commercial sized reservoir. Let's knock our gas saturation. No, that's all right. Gas.
Area.
Huh?
Area.
Yeah, but still you have 1 well per mile. So commercially, you should have enough gas per square mile for a commercial reservoir. Okay? So let's rush to judgment here. What's a recovery factor? How much can I get of that?
80%.
Huh?
80%.
How much of that gas can I recover?
80 to 90%.
When we had low-hanging fruit, we could recover 80 to 90% of the gas reservoir, okay? So let's look at the calculations we used to make for low-hanging fruit. Everybody's familiar with that term right now, right? Okay, so what is the pressure at abandonment? What is the reservoir pressure at abandonment? Okay, keep it in mind, you see that as the pressure goes down, it's like, looks like your sink or your bathtub, you know, there's toward the drain, toward the wellbore, so. And at some PWF abandonment, there's also some average pressure abandonment, okay? So first of all, we've got to have some finite pressure at the bottom to push the gas up to the surface, okay? So we got to fight gravity going uphill, and I'll just kind of give away that except for it's not going to help us too much, but oftentimes we'll use 10% of the depth, but I never gave it a depth. But let's just use a number so we can figure out how to get a number like he said. Who can guess what an abandonment pressure is?
300 pounds.
300 pounds. Okay. Now, volumetrically, again, this is kind of a static equation, but volumetrically, do we have it in our textbook? I don't mean to use the word volumetric. I'm trying to use the equation of material balance. By only doing 3 chapters, I have to embed a bunch of other stuff in here. Yeah, see, chapter 10, material balance. I won't get there by trying this, but we can get close. That's what we're going to be doing here, decline curve analysis. And then here's volumetrics, and then I'm going to look for P over Z. And I found it. So this is in your textbook on page 236. What?
I noticed your BG, the value of your BG is kind of different.
I can't hear you. I got this computer hums down here. You're gonna have to shout it.
I noticed the value for your BG.
You don't get my value?
Not that, I don't get it, but it's not that exact.
Can you highlight what you clicked on?
Maybe I did it
Yeah, that
wrong.
one, yeah.
So you give the different specific.
Pressure's 5,000, temperature's 160, gas gravity is 108. That's just 108.69. That's
So
this
you're
number over
using
here.
that number.
And then I gave it 0 for all the impurities.
Okay.
But I gave-
I'm
Your
getting,
value
what
was
do you do different?
Zero point zero zero
Using
three
gas
three
gravity of 1.08. That's cheap.
48.
Yours is?
That is mine.
Wait. He's using 160 instead of 180 on the temperature. Do you have 180 or 160?
I won't say it. My BG is 0.03348. Yours is 0.3337.
Well, the gravity, like, is it the exact same gravity?
What about this number? Let me add some significant digits here. Did you use 1.0869?
Yeah, I did use everything. And I mean, your value is 0.003337. Mine is 0.33.
Are you using a mat? That's a joke.
So is
I
that
mean,
what
your
we're supposed to
screen,
use
your
for G,
screen
is
should
the
look
gas
just like
gravity?
mine right here.
Yes.
If you got 5,000, 160, 1.0869, 301, 0, and you get a different result right here.
No, I got the same result, but on your screen it's different. My result is 0.003348.
So smart.
Okay, easy is 3337.
How about if I cut off a significant digit there?
Okay, that works.
Everybody happy?
Yeah.
We don't know anything past 2 significant digits in petroleum engineering. I can answer your question that I've got some software in here that's left over from last year. Oh, I can tell you what it probably is. It's probably the difference between using 14.65 and 14.73 for pressure standard conditions. Which, like I said, gets lost in the 4th decimal point. So all I gotta do is change that. So we might not be on the same page here. We can take a look at what I'm doing. So I'm doing that with this utilities. And my gas BG is, my coefficient is 0.0282. But you should have the same thing. Oh, the other thing that can happen is sometimes I use 460, and sometimes I use the more accurate number, 590.
Okay, I think it's from there. 0.282 minus 0.
This could be, some people, this could be, instead of 460, this could be 459.67. But Again, I think that I made this one for you, I don't know what, because this software I never all, so the Z could be the same. But you know what, let's check our theories here. Let's see what we get for Z. Yeah.
Are they dividing by an additional 1,000 in that equation as well?
There's what?
On the OGIP, if you look at the equation, there's another slash.
Oh, are you kidding me? That's why.
That's why it's small.
That's why it's small, so.
So it's
that'd be
already-
me that did this. Original gas replacement, look, and I
It
got
says-
units of MCF.
Which is 1,000.
Yeah.
Divided by 1,000.
Yeah, so.
Thank you. You saved me. And so, if I want BCF, I divide that by 1E6. Okay, so let's go back to a 30-foot reservoir. Okay, 24 BCF. You know, I knew there was something suspicious because it didn't look like a commercial reservoir and it should have been.
So you divide by what? BCF?
What?
Divide.
Now, well, I divided MCF, 1,000 MCF, by another million. 1,000 times a million is a billion.
I'm really not impressed with this programming, because it doesn't tell you what
I'm
units
good at
to
that
input.
one.
Well, yeah, he gave me the thing to look up to tell you. If I find it, I'll send it to you.
I mean, he gets half the points for saying that the units are in MCF, so the input units are.
Okay, everybody done fumbling? Okay, pressure abandonment. I want Z at abandonment, and then we're going to go back in our textbook and we'll figure out why we want that. So, these are just shortcut tricks here, but I'm going to make this all absolute with one F4, so that when I copy that down to here, I'll get the exact same number, but then instead of using that pressure, I'm going to drag it down and use that pressure. Except for I put this in here. Okay. Now, for both of these, I need P over Z. I'm going to call this PI over ZI. That's pretty straightforward, isn't it? And this I'm going to call P abandonment over Z abandonment. And Z's don't have a big factor. They're 0.95 here. Oops. And they're 0.91 here. Not a huge impact. So let's go back to our, oops. Let's go back to our P over Z. Now, it's a linear relationship, not with pressure, but with P over Z. If we had an ideal gas, and we had, because Z's 1, right?
Mm-hmm.
If we had an ideal gas, then as we produce the reservoir, that's cumulative gas produced, G sub P is cumulative gas produced, then our pressure would decline in a straight line. That's just the ideal gas law. That's this first homework problem, or first problem we did in class with the piston, okay? But with the piston, we actually were, because we knew the volume and the pressure, we were able to calculate Z. Here, we're calculating Z from fluid properties. We know the pressure drop is from 5,000 to 300. So now there's a linear relationship. So from P over Z to P over abandonment, 1 minus that is the recovery. Okay, so let's do that.
Because we professor, how do we get the abandoned?
Huh?
Abandoned Z factor, how do we get the Z abandoned?
You're trying to catch up with me, is that what you're doing? It's a function that's reservoir temperature, pressure abandonment. Oops, wrong thing.
I don't think we're getting the same.
Not again. Well, all I gotta do is get rid of some of these significant digits, and maybe then we can agree. How about that?
Our Z abandoned is about 108856. We use the same number as.
At 1/6, maybe I, no, good enough.
Oh, yes, exactly. Sorry about that.
Okay, I'm okay?
Yeah,
All right. All you need to know about reservoir engineering. See if we can't get an equation on here. And here's an example showing data points. You shut it, you produce the well for a while, and you shut it in, and you measure the pressure. You produce the well for a while, and so if you plot P over Z, you should get a linear trend. And it should extrapolate to your gas in place. This is material balance. We're skipping chapter 10, so I'm embedding what we need to know. And there's that horrible unit, MMSCF. Okay, so I want to go the other way. I want to, knowing P over Z at abandonment, I want to know how much of the gas I'm going to produce. So let's mark this slide up, which is easier to do here with my pen. So here's P over Z at abandonment. And I'm going to draw a line here. Okay? So this over this is my recovery factor.
How could you tell by looking at that specific plant was the pressure abandonment?
We guess the pressure abandonment,
Gotcha.
okay? And we got plenty of time tonight because this is a long class. Well, we'll look at, it gets kind of complicated because at some point in time, I have to be producing at a commercial rate. And that rate has got to sustain the cost of the operation of running that well. So let's say that's 10 MCF a day. That's a pretty low rate. But at $4 an MCF, that's $40 a day. And at that's $1,200 a month. And maybe I can pay a part-time pumper to go out there and take care of that operation. You know, it's a pretty low rate. But at 10 MCF a day, there's some friction and some gravity loss. And then also I'm feeding a line which might even be 300 PSI. But let's say I'm feeding a low pressure line that's maybe 50 PSI. But I can make a calculation in chapter 4 which we're skipping. So we'll embed a little bit of it tonight. There's some rate that there's some pressure and rate at the surface that will translate to a bottom hole flowing pressure. And then that bottom hole flowing pressure, which you can see is PWF on this graph, isn't the abandonment pressure at all, because there's a cone that moves out. So the average reservoir pressure is lower than that abandonment flowing pressure. Okay? But we can kind of get close to these numbers through different techniques. Okay, so does everybody see that the recovery, if that red dot is my abandonment, P over Z, that my recovery is my first brace divided by my second brace? Okay? Wouldn't you say that that's the recovery factor? Okay, so since this is a straight line, that's equal to, oops, where's my glasses, where's my pen? Okay, here's my pen. That's equal to this over this, which is I think the way we do this is with a 1 minus. That's why I was hoping to find the equation. 1 minus
Well, he was asking us like we should already know.
P over Z at
I've
abandonment
been talking about previous.
Well, you guys know.
divided by P
But
over
I
Z
didn't miss something there.
is our recovery
It's
factor.
basically a fraction of what you recovered over what's total in place.
Is equation 10.28 not applicable?
Well, okay, then what does that G stand for?
10 what
Gas.
page?
The page
Gas as
before
in, it's in
that.
volume?
Or
Yeah, the volume GP is
235.
gas produced and total G is the entire gas
Okay.
in the reservoir.
Okay, yeah.
So it's just a
Up
fraction.
one more.
So he said 80%. That means
Oh, okay.
say you got
Right up a
1,000.
little bit more.
You're gonna have a recovery factor of 80. You're
Yeah.
gonna produce 800.
Gotcha.
It looks like it's
The,
related
the, this is really funny nomenclature.
One more up.
Okay, there we go. So G sub P over G is our recovery factor. And you can do it as B sub G over B sub GI, but everything is a constant except for P over Z. Nothing else changes in B sub G except for P over Z. So that can be G sub P equals G times 1 minus, and instead of B sub GI, P over ZI. Or is it Z over BI? I think that since B sub G is inversely proportional to P over Z, then it's G sub P equals G, or G sub P divided by G, which is the recovery factor, equals 1 minus P over Z divided by P over ZI. Anyway, we're going to get it here numerically. It's going to be about 80-90%. We know it is. I think it is.
At 94%, that's inside.
Okay, is equal to 1 minus P over Z at abandonment divided by P over ZI. That's my first guess, 93%. 94%. Okay, I can tell you right now, we've never produced more than 94% of any gas reservoir. If you got 5,000 PSI, you're at 8,000 feet. And typically, so let's just add in here, depth. 8,000 feet. Okay, using a gas gradient of 0.1 psi per foot, zero surface pressure would give us equal to 0.1 times our depth. So we're already up to 800 psi, okay? That's with no friction or flow rate and no line pressure, okay? So let's take that and then bump it times 1.5, just to handle some kind of minimum rate friction and some bottom hole flowing pressure. And see, already we're up to an abandonment pressure of 1,200 PSI and a recovery factor of 63%. Okay? It's kind of fun to play around with the numbers.
Do you think there's something in the macros about the seat? Because my I put in all the right movies, and I'm just getting around with an error. Does it convert the temperature directly for us?
Yeah, it'll add 460 to it. So you're having trouble with Z abandonment?
Well, yeah, because I put in all the right values in the function for it, the answers are coming out. So I'm just wondering whether there's something.
Well, how does your screen look compared to mine right now?
I have everything the same except the piece. I put 300.
Oh, you're still at 300? Well, I can put 300 in here. Can you get an error? You don't get
It
0.91?
just gives me value.
Value,
error.
that means it's having trouble doing something. Typically what that means is you know, if you put in a number, let me show you how you can get value. And is, you see I got 0 in N2, but in M2 I got the symbol CO2. Let's just change this to CO2, okay? That's not a number, that's a label, isn't it? That will probably give me value. So you're accessing something that's starting with a letter rather than something that's starting with a name. Okay, that's how you get value. So that's why I'm saying, does your screen look like this? Do you see
Yeah,
1200, 160? Do you see numbers?
That's what I'm adjusting it now so that it has a dollar sign. So I'm pressing F4 for each of them.
Well, the dollar sign shouldn't make any difference.
Okay. So what makes it different?
But here off to the right's the big thing. You should see numbers up and down.
Yeah, I see numbers up and down there as well, just like you.
Really?
Yes, but this is an equals sign, this is nothing.
Well, let's not worry about it. When we're in the break, we can look one on one.
All right.
Yes.
I'm kind of lost using if you're using regarding the debt. You said something about 8,000 there and it's using 1 PSI by 4,000. I was lost.
Oh, I guess the gas gradient is 0.1 PSI per foot.
Okay.
That's a ballpark guess.
Okay. I mean, can you just go by the calculation? Because you use the value you got given that particular thing.
Are you talking about this calculation I did? I took 0.1 PSI times 1 foot, okay?
Okay.
And then I multiplied by 1.5, and the reason I did 1.5, and I'm just playing around here, but I'm guessing that if you were to try to bump your abandonment pressure up to your average pressure, you know, in other words, you're flowing at some low pressure, which I've already gotten, and then, but your average reservoir pressure is higher than that because there's this cone. So I gave it 2 bumps. Here's my equation up here. I bumped it, 0.1 times 8,000 is my gas gradient. With no rate at all and no friction, then I'm guessing what my bottom hole flowing pressure is. But then that's not my abandonment reservoir pressure because there's this cone and I have to accommodate for that. So that's why I bumped it by 50%. I'm saying that a lot of my reservoirs got higher pressure than that. That's the lowest point in my pressure. I'm making these numbers up. I've made up every number in this column tonight. Or with your help, you'll help me make some of them up, okay? I'm just trying to get an idea how this all works.
What was the recovery factor again?
What?
What did you use for the recovery factor?
I didn't use, we calculated the recovery.
Yeah.
factor.
What did you,
I said it's 1 minus
okay, 1
P over
minus,
Z over,
okay,
P over Z at abandonment over P over ZI.
okay.
All right?
Yep.
And actually 63% gas recoveries, not too bad of a number. I'd say it's almost a little too low for low-hanging fruit. So I would maybe cut my 1.5 down to maybe 1.3. There we go, got a nice round number. I used a fudge factor of 30%, a gas gradient of 10%, and now I'm coming up with a very reasonable recovery factor. Okay? And for tight gas, for the gas that you're going to be hunting for, 40% is a good number for recovery factor. But by and large, when you're working gas reservoirs that we're producing out of today that were not unconventional, 70% is not a bad number. So how much gas are we going to recover?
BCF.
$16, is that what you said?
15.
16.8 BCF. What's that worth? I love having the internet. Oh, you know what? I gotta put natural gas. See, you're learning something right now, because gas, we know in this course, is not the stuff we buy by the gallon. But here's natural gas prices today is, okay, Bloomberg is a good source. And see what crude oil is 100, for West Texas Intermediate's 107. I'm telling you, guys, your careers are gonna be good. Where's natural gas? You guys see it on this page?
You have it in BTUs.
Is it in New York issue?
Up.
Up.
Oh, natural gas, right here, 368.
That's per MMBTU.
We'll just call it MCF for this.
Okay.
Now, I'm gonna multiply it
So how do you get 16.8?
times 16.8 and then multiply it times a million. That's the revenue I'm gonna get. So that's worth $61 million. Huh? I multiplied the gas in place times the recovery factor. See, basically I'm moving, where's my, oh, here it is. That's my red dot. So that's how much gas I can produce. And that, how much gas I can produce based on my gas in place. G is another symbol for OGIP, original gas in place. And I did it by calculating some abandonment pressure, P over Z. And since this is a straight line, it's a simple ratio problem. There's a 1 minus in this equation because it's a negative slope. And so I selecting an abandonment pressure and getting an abandonment Z. I now have an abandonment P over Z, and I then can calculate a recovery factor knowing the P over Z initially and the P over Z at abandonment. Material balance is still somewhat of a static operation. I don't get a feel for the performance of the reservoir. For example, is this a commercial reservoir?
Yes.
Why do you say that?
But it depends on the,
Is it worth
60.
$60 million?
$60 million. Okay, now what were you gonna say?
we have to look what investment we are, trying to make this gas produced. then what are the taxes applied, what are the government policies,
Okay.
rights to pay. So we have to focus on that.
I think you guys are at the opposite ends of this argument.
Yeah.
You're saying it's worth a lot of money.
Yeah.
You say we can cut back on a lot of money with taxes and things like that.
Taxes, investment, capex, OPEX.
Okay,
Yeah. I mean,
my point's gonna be different, but both of your points are valid. What if I told you I could produce, well, and here, I'm gonna make this even more complicated. What if this is offshore?
They can, you know,
This may not be economical. It may cost a couple $1 billion to develop an offshore field. And so it's possible this wouldn't be commercial. Just, yeah, typically we're talking onshore. The most expensive wells I'm looking at these days, multi-frac horizontal, 6 to 9 million, sometimes you run up to 12 million, but you're never gonna run up to 60 million. Okay, but here's the critical issue. Let's think about that volcanic rock I showed earlier. Permeability, okay? If I can produce this over a 10-year period, no problem. What if I told you it took 1,000 years to produce this? You see, your operating costs start becoming astronomical when you're trying to produce a reservoir for 1,000 years. So you have to have permeability. And that's why I'm telling you, chapter 1, what is this, chapter 11 that we're in now with a material balance? This is static information. There's no life to it. It's like looking at a two-dimensional picture of somebody and then comparing to like seeing them in 3 dimension and talking to them and smelling them and getting a full feel. So there's this whole added dimension. That's why most of this course the rest of this course after tonight, we're gonna really spend on chapters 6 and 9. So then we get a feel for how fast we can get it out of the ground, and also both in transient pressure analysis and in transient rate analysis, we get a feel for how large it is.
But our oil and gas calculations, I mean, that's great, because that's static, that's, we know just what's down there. But beyond that, on this calculation, you really need some more info to get good,
Yeah, to find out. And then I want to make another comment on this one right here. We don't even do this anymore. Okay? When we had the low-hanging fruit, the state of Texas required you to shut your gas in twice a year, semi-annually, for 24 hours. Okay? So they'd shut in the well, the pumper would come back the next morning, measure the pressure, turn it back on. They do a calculation that we could do in chapter 4. If we run out of time tonight, I won't even show you how to do it. But if we do, I'll show you how to do it. We'll calculate the bottom hole pressure, and we can make these P over Zs. Because the state of Texas wanted to know how big your reservoir was. And in Oklahoma, they're a little less sophisticated. They only made you do it once a year. And then it came along that sometimes when you shut in a well, it didn't come back on. And so operators didn't like this requirement to do this. And then we started producing shale gas reservoirs, and the model showed it'd take about 87 years for the well to build up to average reservoir pressure. So these techniques only apply to the low-hanging fruit. And that's why I don't spend a lot of time in chapter 11, is because we've already produced all these reservoirs. And the reservoirs you're going to produce, we determine gas in place. And we determine the rate we can produce of that with transient pressure analysis and transient rate analysis. So we can do some type curve matching, and we can see when we have flow regime changes, and we can calculate using everything we've already learned how to do: viscosity, compressibility, Z factors, pseudo pressure. You haven't done any practice in pseudo pressure yet, but we can do all the calculations we need, and this stuff's simple. This is a straight line, but it really only applies today to like Gulf of Mexico reservoirs or huge finds maybe in Africa, and if there's still some new finds in the Middle East. Yes?
Okay, the right point you chose on that line.
Yeah.
Can you please explain why you chose that exact point?
I just guessed it, like I did everything else here tonight.
Okay, so you just choose any one. So I'm trying to get the concept behind it. Like, are you saying like if you had a well that was flowing and that was on the point, then you do the comparisons of field with the
Yeah, I could have made that point anywhere, but my params to show the ratio would still apply. Given a pressure abandonment, then I can calculate the recovery factor. Yeah.
I was kind of plugging things in, and I'm just surprised that if I start plugging in values for my N2, CO2, and H2S, the recovery factor goes up as the values go up.
Well, the compressibility changes. In other words, this is a good point. So he's asking why, if you add impurities, do you get a higher recovery? Let's look at that. Let me follow you along here. Which one helped your recovery factor?
N2, noticeably if it was over 5%.
Let's give it 10% nitrogen. My recovery factor is 70 and it goes to 72%. So, nitrogen acts more like an ideal gas than the hydrocarbon gas does. So, it has a better performance as far as compressibility. You produce some, it expands more than just like, I use methane to talk about methane, but also methane, ethane, and propane. So that could be the case. Now, it's misleading that, where's my, how come I don't have dollars on this? Didn't I have dollars on this earlier? Oh, I see. I gotta go that way. So it's misleading to think that when I change my recovery for my nitrogen from $61 million to 10%, I get $62 million, because the price is not going to be the same. Because the heating value is not going to be the same. So that's where we get back into, we're really selling by the million BTU rather than the 1,000 MCF. Clears everything up for you. Oh, I just embed everything in just a few chapters. Okay, we're all good on that? All right then, I think what I want to do next is look at the air we would have gotten. So I need 2 columns here. I'd like it easier up here. Where's my insert rows and columns? That's what I like. Now let's do this, all these calculations again, starting with Z. Assuming that someone didn't tell you that you couldn't use the separator gas gravity, but you had to add in the gas gravity from your second and third stage, and also your liquid had to be transformed. How different would your Z be? So instead of using 1.0869, I use the gas gravity from the first stage separator of 0.712. Everybody see what I did? I'm telling you, you have engineers everywhere in the world making this mistake. So Z is 1. This error is probably not going to be that big. So I'm always going to say the error is the real number minus what we're getting relative to the real error, the real number. So that's a minus 3%. Okay? Now, I'm going to make quick work of this. PI is K2 is absolute, otherwise it's the number below it. B sub G. I'm going to F4 everything, drag it over, edit it, and drag the correct gas gravity and put in the incorrect gas gravity, okay? And then gas in place. Gas in place is going to be a function of BG. So instead of using the right BG, I'm going to use the wrong BG. This is just a scalar. This is the one I need to switch over here and grab the wrong gas gravity. Too much. Divided by Z. I'm going to keep the same pressure, abandonment, and just copy the wrong Z over. Recovery factor. I think I can just, there's a P over Z right and wrong for initial and after. Both of these will work. I'm going to use the same price. 368 is 22. Okay, so on the bottom line here, we're getting 3%, 4% for those kind of errors. It's not as quite as bad as I thought it might be. Let's see how about gas in place. Yeah, 3-4% error. I'm surprised I'm not getting a little bit more now. Okay, we're going to keep moving with this stuff. We're going to call this the, you can see why I like these, the right and the wrong columns. Okay? And the right columns, just so I can keep track of them.
You want to go over one on that?
What?
Yeah, wrong on your percent error.
Oh, I see. I did everything.
There you go.
Don't be afraid to correct me as I go along. Okay. Let's look at some other things here that we want to look at that we haven't looked at. Let's look at viscosity. And let's look at compressibility. I'm going to switch back. Well, I'm going to use both. Compressibility. I kind of want to go through this because these are all the software you're going to need through the rest of the semester. And I want you to get used to the name, used to the nomenclature, as you're going to see it in the textbook when you're going to be called for it, and used to the VB function that you're going to be, in its name, you're going to use to calculate it. And gas density. So I've tried to give a fairly accurate standard Society of Petroleum Engineering nomenclature for these symbols, their names, and then we'll look at the functions. And we'll do these all at reservoir conditions. So the way, this is not my software, the LSU, the way he symbolized his is he just used UG. But it's actually symbolically, it's mu G. I lost it. So I'll click here, and then click F of X. Do you see the inputs always the same for these VB functions? Pressure, temperature, gravity, and impurities. Now watch this little trick. I'm going to look at ZI. ZI is a function of temperature, pressure, impurities. I'm going to get rid of that 10. And gas gravity. Okay? Now watch this little trick. So ZI, I'm going to copy it. It's going to be 0.95. It's all absolute. And I'm just going to change the spelling to the function mu G. And now instead of Z, I'm going to get viscosity. I hope I lost someone there. It took me years to develop that.
Can you do that again?
I'll do it again. So here's Z, right? Right, I copied it down there, absolutely, so it had all the, you see, I got F4s on all, I got dollar signs on all, from all the numbers and all the things. Now I'm going to change that to compressibility, and let me check. I think that it's just CG, you know? And so if I double click CG and then click up here, again, the beauty of that BPD software is it's taking exactly the same variables in exactly the same order. So all I have to do is change the spelling of the function. I'm deleting Z and adding CG, which is the name of the function. Now I have the gas compressibility, which I usually express in scientific format. Because it's a small number. I usually leave viscosity, it's a small number, but 0.054 is good, and 4.85 times 10 to the minus good. And that's in centipoise, and this is in reciprocal PSI. Viscosity what? Now, I could have done that several different ways. I showed you a third way to invoke the functions. I showed you how to do it, just trying to spell it, looking for user-defined functions. And now I'm showing you that since if you're going to use the same variables over again, it's easier to absolute them, copy the cell down there, and just change the function name. Like I said, I hope I lost some of you because it took me years to figure that one out. Because I'm all about the fewest number of keystrokes. Nah, I wrote that one. But we can do the right one. We can do that for gas pseudo pressure. Okay? PSEUDOPR. I usually put a capital P in here. And I'm going to show two different ways of nomenclature I switched to pseudo pressure as P sub P. And then that way you can do a P, if you got PWF, you can just do PWF, pseudo pressure while flowing. But frequently you'll see M of P, because that's the way it came out. It was M was a function of pressure. Remember I told you the author was just looking for the magical transformation, that he could use all the liquid flow equations if he could just figure out the transformation for gas. And it was M of P, or pseudo pressure. And so I think this is M of P, right? It's M of P. So I can do this same copy down thing again and change the spelling this time to MP. And now I got my pseudo pressure. And it's a big number. It's a good thing I had it in scientific notation. It's on the order of magnitude of pressure squared divided by viscosity. So what does that mean? Let's take my pressure squared and divide it by my viscosity and put it in scientific notation. And I got the same exponent. That's what I mean by order of magnitude. Okay? It's not the same number, because it's an integration problem of the pressure over Z over viscosity, integrated from some low pressure base to that pressure. But it's on the order of magnitude, so that's why I'm saying it's a big numbers times 10 to the 8. Compressibility is a small numbers times 10 to the minus 5th. Okay, so what? M of P.
So this is looks like the Z.
What's your question?
No. My Z didn't work.
Oh, yours didn't work.
So I can't.
Does your neighbor's work? Okay, so it's not me.
But I didn't copy the Z, I just do every function by every.
Yeah, and so you re-put in all the variables again?
Yes.
Yeah.
That's what I did.
I did that for like years after years after years, and I realized I could respell them. So I'm offering you like 10 years of experience, like 30 seconds. I go, why didn't I think of that sooner? I'm determined to do things. Once I start doing something over and over again, it bothers me. I go, there's just got to be a quicker way to do this. Okay, I wrote gas density, so let's go over here and look at our VB. And that was really dumb, but I hadn't thought about how I could have done it in the same way. But you know, just for the heck of it, let's just do that. So these run this way. Let me just copy this. Let's fix gas density. Let's just change it. So pressures first. Temperature second. Oh, I see my paper's moving. Gravity's third, and then our impurities. And I got one too many commas. Okay? Now it's the same order. Pressure, temperature, gravity, impurities. All right, I'll give her this comma out. So now we just oops, what happened We just improved our function so we can do the same thing with gas density. And we don't need any and so what is its liquid gravity? It's about 0.3. That's pretty dense. Okay. And that, do I say what my units are before I make a lateral?
Pound per feet
Pounds
cubed.
per cubic feet. So, I think I have constants in here, don't I? You don't have this. I got the density here, but not density. You won't have this. You can just type in the number. Yeah, I saw it there. DHTO. DH. And it takes no argument. I'm seeing what I got here, so 0.4. Now water gradient has a 0.433. This has 0.4 of that. Okay. So, at reservoir temperature and pressure, this gas will have a gradient of 0.172 psi per foot. Now, I've been throwing around a gas gradient of 0.1 before, but that gas gradient is going to change all the time. But if I have 2 points that I got a pressure gauge at the bottom of this well, and I can see that the gas gradient, the pressure gradient of the fluid is 0.172, I could actually figure out what the gas gravity is. Because only one gas gravity would give me that gradient. You know, the only thing you'd have to type in here is 62.366.
You have to hard punch it in your
You don't have that. 62.4 pounds per cubic foot is the density of water.
We have to punch that in our manual.
What's that?
Should we punch it in our manual? Hard punch.
What?
We don't have that function?
You don't have that, no. But you shouldn't have memorized that the density of water is 62.4 pounds per cubic feet. And then, I'm going to do this a little bit differently. And then, if you ever want to know what the gradient of fresh water is, you just divide that by 12 squared. And this will give you the 0.4331 that we're used to see. So that's just a units conversion from density to gradient. Density to gradient is just a division of 12 squared. Instead of pounds per cubic foot, it's pounds per square inch per linear foot. So now I've converted that, and then I want to multiply it by my more accurate number now. Okay.
How did you get the 0.40?
I ratioed my gas density by the density of water to find its relative density, or That's actually a pseudo-liquid gravity. Although it's a gas, it has a apparent liquid gravity of 0.4. It's 40% as dense as water at atmospheric conditions. In the reservoir, as it gets compressed down there, it's no longer like air in this room. It has a pseudo-liquid density of 0.4 or a gradient of 0.17 psi per foot. So probably what I'll do on the test, which is in 2 weeks, is I'll have a graph of depth versus pressure, and I'll ask you what the gas gravity is.
So,
So it'll be handy to know what the density of water is.
in the reservoir, we're seeing a gas gravity about 0.86. If we take the gas density divided by 29, is that?
No, that's, when you divide by 28.96, which is the molecular weight of air, you get the gas gravity. Okay, but I realize this is really confusing, but the gas gravity is 1, okay? But its density is a function of temperature and pressure. So if I looked at the density measurement here, I would not, and divided it by the density of air at atmospheric conditions.
Oh, yeah.
You see, I'm really mixing apples and oranges. I'm already mixing apples and oranges when I'm using this density of water. I'm trying to get you an idea of how dense this gas, which at standard conditions is no different than the gas in this room, or because the air in this room is at atmospheric conditions. So to think that it has a pressure gradient of 0.17 psi per foot, or has a pseudo liquid gravity of 0.4. In other words, it's 40% as dense as water, which is a lot denser than air. But that's because it's at reservoir conditions.
Will you hover on that 0.17 sound?
So 0.4, I'm calling the pseudo-liquid density. Because the liquid, I should say gravity. Okay, oops, that was on. So any liquid has a liquid gravity. It's relative to the gravity of water. So gasoline that you buy at the gas station has a liquid gravity of less than 1. It floats. And I couldn't think right off what fluid sinks. I can't, but if your liquid gravity is greater than 1, then it would sink. So this floats because the apparent, I should use the word apparent, liquid gravity is 0.4. So it's still lighter than liquid, but it's much denser than air. And you get a feel for this if you reciprocate your formation volume factor. They call that E sub G, expansion of gas, which is equal to 1 over the formation volume factor. So this tells you right away that the gas is going to be 300 times as dense at reservoir conditions than it is at atmospheric conditions. This one?
Yes, sir.
I'm dividing the gas density that we use our VB function to calculate by the density of water at surface conditions to get an apparent liquid gravity. I like that word apparent now better.
Could you explain the expansion of that?
I'm sorry,
Could you explain EG again? It's 300.
B sub G,
EG, expansion.
it's 1 over B sub G.
No,
So
what does
instead-
it mean?
well, B sub G is the reservoir volume per standard cubic volume. So E sub G is the standard cubic volume per reservoir cubic volume. Okay, your gas occupies some amount at the surface and some smaller amount in the reservoir. If you're trying to do a gas in place equation, it doesn't matter which one you use. I could change the form of the equation. So it's just like if you're converting centimeters to inches. There's 2.54 centimeters per inch. If I reciprocate 2.45, that's how many inches there are in a centimeter. I like the formation volume factor as it was written in the earliest textbooks and was used for a long time. Some people like numbers, don't like numbers less than 1, so they switched to E sub G. And then all that happens is your gas in place, equation is, I'm not going to go full screen here, but it's, instead of a B sub G downstairs, it has an E sub GI upstairs. Okay, instead of B sub G being PSC over TSC, E sub G is going to be TSCP over PSC ZT. None of that is necessary to know.
Sir, here.
All you need to know to get through this course is B sub G, not E sub G. What's your question?
On the first day when you were showing gas gravities at the well stream and at the stock tank and then...
What do you mean, the first class? I'm still showing that same stuff today.
You bet.
It's right here.
So what we kind of know here is that the gas gravity at surface and the stock tanks, it's going to be less than the reservoir one that we kind of theorized. And we
Okay,
kinda
right.
said that's
Okay, this is a good point. This number right here is always going to be bigger than this number right here. Because just the way we separate gas out in the separators, these other two gas gravities are always going to be larger numbers because they're at subsequently lower pressures. And I've got to do something with this oil. When I add oil into the gas, and I'm going to make it a richer gas.
So the third stage separator with the 1.08 coming off the stock tank here, and
No, the third
No.
stage has 1.55.
That was the well stream.
The well stream is 1.08,
okay.
1.09.
Oh, I see. Y3 is 1.55.
Yeah. This,
And that's
a lot of the gas that we're selling, in fact, let's put it in percent. We're selling, for every 7,670 MCF, most of it is coming off our primary separator. See, 92%. Only 7% is coming from the second stage separator, and only 2% of the gas based on volume. I'm still adding apples and oranges because these other gases have different gravities. So this is not a mole balance.
gotcha.
But just on an MCF basis, 92% of the gas is coming from the primary separator. That's why we never had the numbers on the other twos. especially that last one, 2%, that's why it's usually vented. Not anymore, because we got more health and safety regulations going on. Our industry is wrapping up that 2% these days. It's still a nightmare in North Dakota. If North Dakota doesn't care if you vent it or not, it's wasteland, okay? Well, I shouldn't say that, there might be somebody from North Dakota that watches this, but what the state wants is the revenue from the oil, and they can't get the revenue from the oil if they wait for the oil operator to hook up a gas pipeline, because it's not gonna happen, because there's just a demand for everything, and you make $25 an hour if you work at McDonald's in North Dakota. So, the state is so anxious for the money, they don't care if that 7% or that 2%. But anyway, not only, it's not so much that these are that big of a deal, you got this stock tank liquid also has to be entrained in that. That's why I'm making the claim. This number is always going to be bigger than this number. I'm sorry, this number. Okay, I'm kind of curious, and then I'm going to wrap up. And I didn't get to how do we calculate a bottom hole pressure, but you can get the idea here. Maybe I'll ask it on the test. We have not, I want to look at this. I am curious to what happens to pseudo pressure when we use the wrong gas gravity. How did I get this 9% in these, weren't these 3% before? What did I do different?
You change the impurities?
Oh, the impurities were only, so they're only 1%. And, but my, all of a sudden, okay, I want to relook at this. We got plenty of time. Let's look at our air. Where did our air jump from 1% to 9%? Okay, we got a huge hit on our low pressure Z's. Do you see that? At my high pressure Z's, I only had a 1% error. But at abandonment pressure, my Z's were drastically different. I have a 34% error in low pressure Z calculation when I used the wrong gas gravity. I knew there was a bigger thing in here somewhere along I was missing. So, yeah, now I'm 9% off on my recoverable gas gravity. So, I don't know what this had. Yeah, the impurities diminished my error. So now I'm back to 0 impurities. So I got a 10% error in that. Okay, now I'm moving along. I want to see what happens to my pseudo pressure. This is the point I'm trying to make tonight. What's more important, statics or dynamics?
Dynamics.
And where is my air? See, the pseudo pressure is never even involved in my statics calculations, right? Pseudo pressure, and let's look at one more. Let's look at delta pseudo pressure. I love coming up here and hitting the symbol. We never got a pseudo pressure at abandonment, did we? I got room for it. I can do a delta pseudopressure is, remember we have a delta pseudopressure is the driving force for our gas to go through our pack. Pseudopressure, I think this is my initial. No, that's not it. Here's my pseudopressure minus the smaller number. Yes, is my delta pseudopressure. Okay, now I need to do this for the wrong gas gravity. Isn't that what this column's for? If I use the wrong gas gravity. Somehow this will all come out in test questions. I don't know how yet. Okay, pseudopressure, and I'm going to get lost here. This is pseudopressure of A, B, D. Pseudopressure at abandonment is this one right here, right? Yep, 1040. And then my delta pseudopressure, which is the driving force of fluid flow in all my dynamics, 41%. Now, we could have lived with that 3% error. Maybe, how about this? I only get a 1% error by using the wrong gas gravity. I know I can work this into a test question. I can only get, I'm only getting a 1% error in a static calculation of my gas in place using the wrong gas gravity. But if I'm doing dynamics, not that one, but that one, where I have the pseudopressure of the external or initial pseudopressure minus the bottom hole flowing pressure, okay? That's what's going to drive my dynamics. And that same equation is in Chapter 9 in transient rate analysis and in Chapter 6 in transient pressure analysis. The error I make with the wrong gas gravity, generates a 41% error, that driving force of delta pseudopressure. Huge, huge error. So if I was trying to calculate how much gas I'm going to get over time, I could be 50% off. Okay. I never thought that was going to work out that well for making up the numbers and going along. But I had known for quite a long time that you have to pin down, because I had seen these errors on students' research reports where they've done the transient pressure analysis or transient rate analysis, and they use the separator gas gravity, and I knew they were way off. All right, I think that's going to wrap it up for tonight, unless there's some more questions.
What is that .17?
A lot of times, if you can tell me, you can just say, what is G31? How about that?
Oh, the
gas pressure gradient?
PSI per feet per foot.
The gas pressure gradient.
The gas gradient.
Oh,
The one I'm doing right here?
Up, no, up.
K.
30.
Here.
Well, that's what's going to be on the test. Given a gas gradient, excuse me, given a pressure gradient. So I'm going to lower, this thing measures the, this is from Radio Shack, and it measures the voltage in my batteries on my microphone. I can check them before class. But there's another meter that we lower into the well that measures the pressure. So if I measure the pressure at two different places, I got a pressure gradient in PSI per foot, right? Let's say I measured the pressure just 1 foot away. Then the difference in those two pressures is the pressure gradient in PSI per foot. if I measured the pressure 10 feet away, remember, it's always getting higher pressure. Then I would, and then I got two pressures, I'd have to divide by 10 the pressure difference to get the pressure gradient in the units of PSI per foot. Working these numbers using the gas density function, I don't have to really know the apparent liquid gravity and to do this calculation. Let me see what happens when I delete this. All I need to know is that the gas density, I'm glad you asked this, divided by 144. The pressure gradient and the density at reservoir conditions are only differed by a unit conversion factor of 12 inches per square foot, or 12 squared inches squared per foot squared. So if I divide any density in pounds per cubic foot by 144, I get the pressure gradient. We can measure pressure gradients. We can measure pressures. And so, hypothetically, there's only one gas gravity. If I'm drilling into a well, and I know the pressure gradient. I like people to know how to do problems forwards and backwards.
So it's more or less like back solving.
Huh?
It's more or less like we're giving the depth and pressure, and we're back solving to get the gas.
Yeah. Frequently, there's ways to make deterministic solutions moving forward. But we can really utilize a lot of these gas PVT and gas utility functions for modeling, like we did the first problem we did in class, where we had to figure out the gas gravity, looking at the experimental results that would give us Z factors as a function of pressure. There was only one gas gravity that matched that data. This is the same kind of work you did, right? That first day of class. So that's what I'm trying to really get across, is that by having these PVT properties, we can model resultant data. Not knowing what the inputs are, but solving for the inputs. And I like this kind of problem with the PVT, and the reason I stress them is this is all we're going to do in Chapter 6 and Chapter 9. We don't know a lot of stuff. There's no deterministic calculations. We model everything. And then after we get a model match, we back extract some things that we didn't know beforehand, like permeability. So where I may be solving for gas gravity by giving you a gas gradient, in Chapter 6 and 9, we're going to be looking at rate time or pressure time data, and I'm going to be asking you to get permeability. I'm trying to ingrain in you the power of modeling and model matching.
Is it all right to say, if you want to use the word dynamic, is it all right when you refer to the pseudo pressure, you just adjust the gas gravity given? You just, because what you did was you changed the G to the gas gravity.
You mean in the right column and the wrong column?
Yeah, where you're trying to like compare them, you're trying to make a comparison, and you termed it dynamic. That was the last explanation. Using the pseudo pressure now as a term.
And basically,
Yeah.
I missed one calculation. We had a apparent error in the pseudo pressure calculation and abandonment of 18%. And I had initial conditions of 35%, resulting in the other direction, in a delta pseudo pressure error of 41%.
So when you ask for something, let's do a dynamic work on this is what you expect.
Well, When we're looking at getting a model match, and right next to where that, let me get my pen out here. Right next to where that pseudo pressure came in is this term K, which is permeability. So we'll see if I'm 45% off on my delta pseudo pressure term, then I'm creating a like term. I'm going to be 45% off too high or too low for my permeability. After I get some kind of match, if I'm plugging in the wrong delta pseudo pressure, that error means what I'm probably going to be doing with this is I'm going to be getting a y-axis match. The unknown in this equation is going to be K, permeability. I'm going to know H. I'm going to know 1422, it's a constant. Q is my production rate in MCF a day. T is my absolute temperature in my reservoir. There's only one unknown in that equation, perm, and I'm going to get it from a y-axis match. But if I put in a delta pseudo pressure that's 40% off, I'm going to calculate a perm that's 40% off. Yeah.
You know how we did the two different well stream specific gravities?
Yeah.
Is the one using the 3-stage more accurate, or is?
I answered this last week.
I know, but
Who can tell me the answer? Which one uses correlations and one uses molecular balances? Okay, I'm just going to have to add that to the test. You should know the answer to that. Figure it out. Read in there.
we did the two different well stream gravities.
No, we did the same well stream gravity.
Well,
we
the
did
two different
ways.
calculations. One where we used the 3-stage separation numbers, and then one where we used the API gravity and the temperature and pressure. And I asked him which one was more accurate.
Oh yeah, it's recording too. All right, I'm going to stop the recording. And that might be the first halfway decent recording we've done.
The last lecture you uploaded in the video, we can see the video, but we can't hear the sound.
I loaded the sound now with it. They're not the same file, but your computer, at least my computer, will play the video and the sound. But then I have to keep adjusting the sound bar so that it's on task with what I'm talking about. It's not real easy to do. If you can do it. Or you can just remember what happened in class. Okay, so next week I'm going to start chapter 6. And then the week after that we have a test over chapter 1. So, I don't want to see you guys between those two classes to ask about chapter 1. If you have any questions about chapter 1, I'm willing to spend the whole 3 hours next Wednesday to answer those questions. After next Wednesday, I'm not going to give you any time. Is that clear?
Let's start with this question.
Yeah. I don't like procrastination. And I'll tell you what, this sounds strange, and I'll explain myself. I don't like students coming to my office to ask about things that are going to be on the test. I think it's unethical. Do you get that? Because if you come to my office, what you're kind of expecting, I'm not really pointing at you, I'm using you as an example.
Why ask?
You're basically asking me to give you information that these people won't have.
Insider trading.
Do you guys get that? It's not because I'm lazy, I promise. It's not because I don't want to teach you one-on-one. It's because I want, if you have a question, I guarantee they need to know it too. And so you have 1 week to figure out if there's anything you don't understand after watching this lecture on chapter 1. And then I'll spend as much time as you guys want reviewing it. Otherwise, I'll be ready to go into chapter 6. Sound like a plan? And it's okay to come by my office between now and next Wednesday. What I'll do is I'll write down your question and be sure to answer for everybody.
So we can email you some questions.
Huh? Or you can just email me the question. I didn't understand this part about that. I guarantee I'll make it a part of next Wednesday's lecture. Okay, see you next Wednesday.